Now, what about reactions that involve ethers? Whether that's how we make ethers or what we can do with them. Well, in both cases, there's not a lot that we have in terms of reactions. And that's because ethers are relatively unreactive. In fact, diethyl ether is one of the most common solvents that we use in the organic lab. And we wouldn't choose something as a solvent if it was going to react when we were doing something. So previously we learned one method for synthesizing an ether, and that was oxymercuration. So mostly we talked about oxymercuration as a way to make alcohols. If you recall, an alkene, we added mercury acetate and water, followed by sodium borohydride, and that gave us a Markovnikov addition of an alcohol. But we said also briefly that we could replace the water in this reaction with an alcohol. And if we replace the water with an alcohol, then in the step where the three-membered ring containing mercury opens, instead of water forcing it to open, ethanol is what forced it to open. And that was one way of synthesizing an ether. But probably the most common method for making ethers is one of the oldest known reactions we have, known as the Williamson ether synthesis. And the Williamson ether synthesis dates all the way back to 1852. Now, this is a good example of a reaction that we're presenting, as a new reaction with its own name. Yet, this reaction contains nothing new. What do I mean by that? Well, the Williamson ether synthesis is going to allow us to take an alcohol, and in two steps. First, we add sodium hydride, which is a strong base, and then we add some sort of alkyl halide. And that forms this new carbon-oxygen bond and forms our ether. But again, both steps involved in this reaction are steps that we've seen many other times previously. So how does this reaction work? What's the mechanism? Well, sodium hydride is a strong base. And while alcohols are typically not good acids, if we add a base as strong as sodium hydride, it's going to be good enough to deprotonate. And so if we deprotonate that oxygen, we end up with this anion. And then the anion does nucleophilic attack on the R group, kicking out the iodine. And so two steps here. The first one is just an acid-base reaction. And the second step, you can see we have a nucleophile attacking an electrophile, simultaneously kicking out a leaving group. So hopefully at this point we recognize that as a typical SN2 reaction. So again, while this is one of those reactions that has its own name and we list it like it's a separate reaction, everything about this reaction's mechanism is something that we've already learned. Now, we do have to be careful with this reaction. Because it's an SN2 reaction, all of the things that we learned that apply to SN2 reactions still apply here. So in other words, let's say we wanted to make this compound. This is known as MTBE, methyl tert-butyl ether. It's a compound that's added to gasoline to try and reduce carbon monoxide emissions. Now, how would we make this from a Williamson ether synthesis? Well, we can cleave the ether in two ways. We can cleave it on this side, or we can cleave it on this side. And then we can go backwards to see what the starting materials would be in each case. If we cleave it on the left side, which is the line I've drawn in red, that means we would start with methanol plus this alkyl halide. So that means once we deprotonate methanol, it would need to do nucleophilic attack onto this tertiary alkyl halide. And one thing we emphasized a lot in the SN1, SN2 chapter is, if we have a tertiary leaving group, for all practical purposes, we see no SN2 reactions. So that method's not going to work. But if we do it the other way, then our nucleophile is on the more complex starting material, and we have a primary alkyl halide. And that, we know, a primary leaving group will work very well for SN2. So again, this is the most common way that we have for making ethers, but it's really just an application of an SN2 reaction. So all of the things that we learned that mattered for SN2 reactions, we have to take into account for the Williamson ether synthesis as well.